Prime numbers. You definitely remember them from math class, right? But they're also one of the deepest, most enduring mysteries in all of science. So what if the secret to their pattern isn't just random chance, but a kind of hidden order? Let's dive into a really fascinating new theory that might, just might, finally be cracking the code.
So just a quick refresher. Think of primes as the absolute building blocks for all other numbers. I mean, every whole number out there can be broken down into its own unique product of primes. They really are the atoms of arithmetic. They're indivisible, and we've known for centuries that there are infinitely many of them.
But here's the puzzle. The thing that has kept mathematicians up at night for, well, forever. If you just list them out, 2, 3, 5, 7, 11, 13, and so on, they seem to pop up without any rhyme or reason. There's no obvious pattern. So what is it? Is the sequence totally random? Or is there some kind of hidden order that we just haven't been clever enough to see yet?
Well, a pretty groundbreaking new paper is suggesting the answer might be neither of those. It argues that the secret of the primes, it isn't governed by random chance at all. Instead, their mysterious, beautiful pattern might actually be the direct result of something called deterministic chaos.
You see, for a very long time, the best tool we had for studying primes was probability. The prevailing idea was that whether any given number is prime or not is, well, it's basically like a cosmic coin toss, just with the odds changing a little as you go up the number line. And this leads to what this new paper calls the density paradox. It's a really cool idea. If you zoom way out and look at primes from a distance, they look pretty random, and probability can tell you roughly how many you'll find. But if you zoom in close, they follow these super rigid, unbreakable rules. Like for instance, besides the number 2, no prime number is ever even. A truly random coin toss would never ever produce a strict pattern like that. And this comparison really nails the problem. On the left, you've got the old random chance model. Yeah, it's pretty good at estimating density, the how many, but it completely fails to explain the underlying structure, the where and why. But now, look to the right. This is the new idea, deterministic chaos. It's a model that says primes come from a simple, predictable system that can explain both things, their density and their rigid structure. It bridges the gap. Okay, so how in the world do we get from prime numbers to chaos theory? The trick, it turns out, is to completely reframe the question. What if we stop thinking about this as a pure math problem and start looking at it like a physics problem? It all starts with something you probably did in school, the sieve of Eratosthenes. You list out all the numbers, then cross out all the multiples of 2, then all the multiples of 3, and so on. Whatever's left standing, those are the primes. But here's the new twist. Instead of just crossing numbers out, let's create a sequence. We'll label a number L for alive if it's still in the running, and R for removed. So, sieving for 2 creates a really simple pattern, R, L, R, L. But then, when you layer on the sieve for 3, those patterns interfere, and you start to get a much more complex, almost wave-like sequence. And this flowchart, this is really the heart of the whole theory. On the left, you have that sieving process we just talked about, which turns simple arithmetic into a symbolic sequence of L's and R's. Then, and this is the leap, that sequence is mapped directly onto a famous chaotic system from physics. The big idea here is that these two things, the prime sequence and the chaotic system, are basically just two different languages describing the exact same underlying dynamic process. So what is this specific chaotic machine that's supposedly spitting out the primes? Well, it happens to be one of the most famous and well-studied systems in all of science. This is the logistic map. It's like a visual blueprint for how simple systems can become chaotic. What the researchers did was brilliant. They basically drew a line down the middle of this map, dividing it into two regions. If the system's value lands in the L area, that corresponds to an alive number, a potential prime. If it lands in the R area, it's a removed number, a composite. Now here is the absolute kicker. The prime sequence doesn't just map to anywhere on this chaotic landscape. No, the theory shows that the entire secret to the primes, it all lives at one single, incredibly precise location. It's a special parameter value known as the edge of chaos. And it makes perfect sense, right? It's that perfect sweet spot, a system that is complex enough to look random, but still contains a deep, profound underlying order. Just like the primes themselves. Okay, that's a wild claim. I mean, it's a beautiful idea. But to really believe it, we're going to need more than just a cool theory. We need hard evidence. And honestly, the evidence the paper presents is genuinely stunning.
So check this out. On the left is the fingerprint of the real prime numbers. It's a chart showing the frequency of gaps between them. See those distinct, spiky peaks? Now look at the right. That's the fingerprint generated by the chaos model.
I mean, wow, the resemblance is uncanny. It doesn't just look similar, it spontaneously reproduces the exact same peaks, including a really deep feature of primes related to multiples of 6. That was supposed to be a rule of arithmetic, not physics.
So then they dug into the dynamics. This chart here, it basically measures how predictable the sequence is from one step to the next. That gray line at the bottom, that's true randomness, totally unpredictable. But look at the blue line from the real primes and the red line from the chaos model. They overlap almost perfectly. They both show the classic telltale signature of what's called low-dimensional chaos, a system that looks random but is actually following very precise, predictable rules underneath.
But maybe the most powerful piece of evidence, the real clincher, comes from a famous, almost mythical number in mathematics, the twin prime constant. This number, it's this very specific value that describes how often we should expect to find twin primes, pairs of primes that are only separated by 2, like 11 and 13. And here it is. The researchers just let their chaos model run, and they used it to calculate the twin prime constant from scratch. That red dashed line is the true, known value. The green line is what their model calculated, and as you can see, it converges on the correct value with just astonishing precision. And the most incredible part? They didn't have to tweak anything. There was zero tuning, no fudging the numbers. The right answer just emerges naturally from the system's dynamics. This, right here, this is the smoking gun. So, what does all this mean? I mean, if this theory holds up, it really does represent a fundamental paradigm shift in how we understand the most basic objects in all of mathematics.
So let's break down the big takeaways. First, and this is huge, prime numbers are not random. It seems their mysterious pattern is the predictable result of a simple, chaotic system. And this builds an incredible new bridge between the abstract world of number theory and the very real physical world of dynamics. So that randomness that has puzzled geniuses for 2,000 years, it might actually just be a very specific, very structured type of weak chaos.
The paper's author really says it best. The distribution of primes is the trajectory of a deterministic system evolving at the edge of chaos. It's just a beautifully simple and elegant explanation for one of the most complex problems we've ever faced.
And all of this leaves us with one final, tantalizing question. If the oldest mystery in mathematics can be explained by looking at it through the lens of physics and chaos, well, what other deep mathematical mysteries, what other hidden patterns might be hiding out there, just waiting to be discovered in the language of chaos?